In January 2026, astronomers confirmed a galaxy that should not have existed. It was not supposed to appear so early. It was not supposed to shine so brightly. It was not supposed to look so chemically mature when the universe itself was still young. That is the first correction tonight. The early universe may not have behaved the way our models said it should. This galaxy comes from 280 million years after the Big Bang. In cosmic terms, that is infancy. If the 13.8 billion year history of the universe were compressed into one calendar year, this object would appear in the first days of January, and yet it already looked older than it should. Then came the second crack. For years, cosmologists have argued over a vital number, how fast the universe is expanding. One method points near 67, another keeps landing near 73. The gap sounds small. It is not small. In precision cosmology, that difference is the space between confidence and crisis. And that is the second correction. A disagreement that looks tiny on paper can become enormous when it sits at the foundation of reality. If that number is wrong, then the age of the universe shifts, the scale shifts, the growth of galaxies shifts, the future shifts. One number moves, and the whole map trembles, like learning your house was built on a fault line. So tonight is not about a simple question like how big is the universe? It is about something unsettling. What if our map is wrong? What if the framework we use to explain expansion, structure, and cosmic history is starting to strain under better data? What if the universe is not just bigger than we thought, but stranger in the way it is built? Tonight, we move outward in stages, from Earth to the Moon, from the Moon to the planets, from the planets to the stars, from the stars to the Milky Way, from the Milky Way to the voids, the cosmic web, the horizon of light, and the dark machinery beneath it all. Each step will make the last one feel small, and that leads to the third correction. The universe is not simply a larger version of the world you know. It plays by rules your intuition was never built to handle. Distance in the cosmos is not like distance on Earth. Empty space is not just empty. Darkness is not just the absence of light. Expansion is not just motion. At cosmic scales, these are structural forces. They decide what can meet, what can form, what can be seen, and perhaps what can never be reached. For a long time, our story felt reassuring. First we learned that Earth was not the center. Then we learned the Sun was a star. Then we learned the Milky Way was one galaxy among trillions. With each step, the universe grew larger, but the pattern felt stable. But sometimes clarity is only temporary, because now the facts are beginning to resist the story. The oldest light in the universe tells us one thing. Nearby galaxies tell us another. The early cosmos should have formed structure slowly. Yet James Webb keeps showing us objects that look too bright, too massive, or too mature for their age. The standard model still explains a great deal. That is why this moment matters. We are not watching a weak idea fail. We are watching a powerful idea meet data sharp enough to wound it. That is the fourth correction. Science does not become fragile when it knows less. It becomes fragile when it starts seeing more. Cosmology is not a pile of separate facts. It is a chain. If the expansion rate changes, the age changes. If the age changes, the timeline of galaxy formation changes. Pull on one link, and the tension runs across billions of light years. That is why this is not just an astronomy story. It is a story about confidence. Most people carry a picture of the universe in their heads. The stars are far away, but understandable. Space is vast, but mostly mapped. Science may not know every detail, but it knows the outline. That picture feels calm. It feels like standing in a room with the lights on. But what if we are not in a room with the lights on? What if we are in a much larger house, holding a flashlight, and only now realizing the walls do not end where we thought they did? That is the feeling of this moment in cosmology. Not ignorance in the old sense, something stranger. A growing suspicion that the dark beyond the beam is larger, deeper, and more structured than expected. Because the moment your map becomes unstable, your sense of place becomes unstable too. If the structure of the cosmos is harsher than we assumed, then the question of whether we are alone may not be about life at all. It may be about architecture. Maybe the universe is not merely hard to cross. Maybe it is built to keep things apart. That idea sounds dramatic now. Before this night is over, it may sound practical. So this is where we begin. Not with comfort, but with a warning. Not with a finished diagram, but with stress lines running through the blueprint. And the first lie reveals itself the moment you look up at the night sky above. Go outside on a clear night. Find a place far from streetlights. Let your eyes adjust. Wait, then look up. What you will feel is immediate. The sky seems deep, crowded. It feels as if the universe has opened above you. It has not. That is the first correction. The night sky is not the universe. It is your neighborhood pretending to be everything. On a very dark night, a human being can see roughly 4,000 stars with the naked eye. That sounds like abundance. It is not abundance. It is a tiny handful. The Milky Way alone contains about 250 billion stars. Seeing 4,000 of them is like standing in a city of glass towers and spotting a few lit windows, then thinking you have seen the whole skyline. And even that comparison is generous. Most of the stars visible to your naked eye lie within about 1,000 light-years of Earth. 1,000 light-years sounds immense, but the Milky Way is about 100,000 light-years across. So when you look up, you are not seeing the galaxy. You are seeing roughly the nearest 1% of its diameter, a thin local patch floating inside a system far larger than your senses can hold. That is the second correction. The stars above your head do not show you the cosmos. They barely show you the street you live on. Now widen the frame. The Milky Way is one galaxy. The observable universe contains an estimated 2 trillion galaxies. Not millions, not billions, trillions. If the Milky Way were a single grain of sand, the observable universe would not be a beach. It would be a shoreline so long you could walk your whole life and never reach the end of it. And each one of those galaxies contains stars. Astronomers estimate there are around 10 to the power of 24 stars in the observable universe, a 1 followed by 24 zeros. Numbers like that do not land naturally in the human mind, so let us shrink it into something you can feel. Every star you have ever seen is less than a spark from one neighborhood inside, one city on one grain of sand in a desert of galaxies. That is the third correction. The night sky feels infinite, only because your brain is good at being impressed, not at measuring scale. This matters because the illusion of the night sky is emotional before it is scientific. It tells you that what you see is almost everything. It gives you a false sense of contact. You look up and feel connected to the cosmos, but most of reality is missing from view. Not hidden by mystery, hidden by distance. And distance already changes everything. If the universe were simply large, that would already be hard enough. But cosmology is not only about size, it is about motion. The entire universe is expanding, and the number that describes that expansion is one of the most important in physics. It is called the Hubble constant. You do not need the equations yet. You only need the consequence. Get this number right, and the broad story of the universe holds together. Get it wrong, and the age of the cosmos shifts, the scale shifts, and the growth of structure shifts with it. It is not just another measurement, it is a master dial. For decades, scientists have had two main ways to estimate it. The first uses the ancient light left over from the early universe, the cosmic microwave background. That signal comes from a time when the universe was only about 380,000 years old. Cosmologists use it like a fossil imprint. Read the pattern correctly, and it tells you how the universe should have expanded over time. That route gives a value near 67 kilometers per second per megaparsec. The second route uses the nearby universe. Astronomers measure distances to stars, then to farther stars, then to galaxies, building what is called the cosmic distance ladder. That method keeps giving higher answers, around 73, sometimes even more. 6 units may not sound dramatic, but this is not a loose estimate. It is like measuring the same human heartbeat with 2 perfect instruments and getting 2 different rhythms. That is the fourth correction. In cosmology, a small numerical gap can be a warning flare. For years, people hoped the problem would fade. Maybe dust was skewing the data. Maybe the instruments were imperfect. Maybe some hidden calibration error would close the distance between the 2 answers. But the disagreement has not gone away. It has sharpened. New observations have kept pressing the same wound. James Webb has rechecked key local measurements with cleaner infrared vision. Independent methods, including gravitational lensing, have leaned toward the higher local value. The old hope was that the universe would settle the argument for us. Instead, it has made the argument harder to ignore. That is the fifth correction. When better tools fail to remove a contradiction, the contradiction becomes part of the message. And that message is dangerous, because the Hubble constant does not live alone. Change it, and you change the inferred age of the universe. Change the age, and you change the timeline of galaxy growth. Change the timeline, and objects can appear too early, too bright, too evolved. So this block is not really about stars. Not only about stars, it is about trust. The night sky trains you to believe that reality is laid out cleanly above you. Bright things seem close to truth, stable patterns feel reassuring, but the real universe does not owe you a simple surface. The visible sky is a thin layer. Behind it sits a much larger structure, mostly unseen, measured through inference, and now beginning to resist the model we used to describe it. The deeper lesson is uncomfortable. Human beings evolved under a local sky. We are excellent at reading weather, motion, brightness, and horizon. We are terrible at intuiting trillion galaxy reality. So when the sky tells you that you are looking at everything, it is not just incomplete, it is misleading in a way that feels natural. That is why this lie is so powerful. It arrives as beauty. The stars do not look like a trap. They look like revelation. But they reveal only enough to make you underestimate what surrounds you. And once you understand that, another thought should begin to form. If even the visible sky can hide this much from us, what happens when we point our best telescopes toward the first galaxies and discover that they, too, are refusing to behave? The crisis becomes real the moment it has a face. A strange number on a graph can still feel abstract. A disagreement between two measurements can still feel distant, but a galaxy is harder to ignore. And when that galaxy appears too early, too bright, and too developed, the argument stops sounding technical. It starts sounding physical. That is the first correction. We are not talking about a small bookkeeping error. We are talking about objects that seem to have arrived before the universe was ready for them. One of the clearest examples is a galaxy called MOM Z14. Its light comes from about 280 million years after the Big Bang. That number is easy to hear and hard to feel, so shrink cosmic history again. If the universe were a single year old, this galaxy would appear in the first week of January. It should have looked raw, dim, and primitive. It did not. MOM Z14 was brighter than expected, more chemically enriched than expected. Astronomers found signs of nitrogen, an element that usually takes multiple generations of stars to build up. Stars must form, die, explode, enrich the gas, and then new stars must form from that enriched material. But time was exactly what the early universe was supposed to lack. That is the second correction. The early universe was not supposed to be old enough to leave fingerprints of maturity. There was another problem. This galaxy seems to have already altered the space around it. In the early cosmos, neutral hydrogen acted like a thick fog. Ultraviolet light could not move freely through it. Yet MOM Z14 appears to have begun clearing that fog in its local region. That is like finding a campfire already burning in a forest that should still be soaked from the rain. One strange object can always be dismissed. But James Webb did not find only one troublesome case. It kept finding more. That is the third correction. The problem is not an exception. The problem is a pattern. Before Webb launched, many models predicted that bright galaxies at redshifts above 10 would be rare to the point of near absence. The early universe should have been populated mostly by small, faint systems still beginning the slow work of assembly. Instead, Webb started returning a sky crowded with candidates that looked brighter, more numerous, and more evolved than expected. Not slightly more, dramatically more. In some ranges, the number density of bright galaxies appears more than 100 times higher than pre-launch expectations. That is not a gentle correction. That is not moving a chair a few inches to the left. That is walking into a room and discovering the walls are in the wrong place. Another case sharpened the tension. A galaxy called Zhulong appears about 1 billion years after the Big Bang. That is older than MOM Z14, yes, but still early for what it seems to be. Zhulong is not just luminous, it appears structured. It shows features like a mature spiral galaxy, with a central bulge and organized form. It looks less like a cosmic infant, and more like something that has already lived through a long adolescence. That is the fourth correction. The issue is no longer just brightness, it is maturity. And maturity is expensive. A galaxy does not become massive, organized, and chemically enriched for free. It needs star formation. It needs gas inflow. It needs time for generations of stars to live and die. It needs structure to settle. When you see those features too early, you are not just seeing an object. You are seeing a timeline under stress. The standard cosmological picture, lambda CDM, still explains many major things well. It explains large-scale structure. It explains the cosmic microwave background with stunning precision. It explains why dark matter must exist to help seed structure. None of that disappears because James Webb found difficult galaxies. The Big Bang is not collapsing here. The background radiation is still real. The expansion of space is still real. The abundance of light elements still points to a hot early beginning. That is the fifth correction. The question is not whether the universe began hot and dense. The question is whether it built complexity faster than our model allowed. Several ideas have been proposed. Maybe star formation in the early universe was far more efficient than expected. Maybe gas collapsed faster. Maybe supermassive stars enriched their surroundings unusually quickly. Maybe dark matter behaved differently in the young cosmos. Maybe early dark energy briefly changed the pace of structure growth. Each proposed fix solves part of the problem and risks creating another. Increase star formation too much, and other observations become harder to fit. Add new energy components, and the cosmic microwave background must still behave. Change dark matter physics, and you may disturb the large-scale structure that already works so well. You cannot patch one wall by breaking three others. And that pressure matters beyond technical cosmology, because what Webb is showing us is not just a collection of exotic objects. It is a warning about how reality behaves when we finally look at it with sharper eyes. For years, the distant universe lived mostly inside simulation and elegant expectation. Then Webb arrived and asked the oldest scientific question in the harshest way possible. Are you sure? That is the sixth correction. A theory can look complete right up until the universe answers back. And there is something unsettling about the style of that answer. These galaxies are not failing in random directions. They seem to be too early, too bright, too massive, too enriched. That is exactly the kind of consistency that makes scientists lose sleep. Random chaos is annoying. Coherent contradiction is dangerous. If galaxies formed faster than expected, then our assumptions about the early universe may be incomplete. If complexity came earlier, then the clock of cosmic history may need to be read differently. And if that clock shifts, then the tension does not stay trapped among the first galaxies. It spreads outward into everything tied to time, growth, and expansion, which means this block is not really about distant objects alone. It is about the moment the young universe stops behaving like a rough draft and starts looking like it skipped ahead in the script. And once you feel that, another truth becomes easier to accept. The cosmos is not only large, it is hostile to intuition. Even our nearest celestial neighbors already strain human imagination. So before we go farther, we need to do something simpler and colder. We need to feel what distance itself does to us. The easiest mistake to make in cosmology is to think that the real problem begins far away. It does not. The problem begins close to home. That is the first correction. You do not need to leave the galaxy to feel how hostile the universe is to human scale. You only need to start with the moon. The moon looks near. It hangs above us like a companion. It appears close enough to touch. But the moon is 384,400 kilometers away. You could line up roughly 30 Earths between here and there. A rocket needs 3 days to reach it. Our nearest celestial neighbor is not a quick trip. It is already a crossing. And that matters because the moon is the easy case. Mars is the planet we speak about when we talk about the future. Colonies, human footsteps, a second world. In the best conditions, Mars can come within about 55 million kilometers of Earth. In worse alignments, it sits more than 400 million kilometers away. The average distance is around 225 million kilometers. That is not another country. It is a gulf so wide that even light needs time to cross it. A radio signal takes between about 3 and 21 minutes to travel one way between Earth and Mars. That means no real conversation, no fast rescue, no ordinary command and response. Even if both worlds were full of people, they would speak like ghosts, using delayed echoes across a canyon of space. That is the second correction. Our next door planet is already beyond human immediacy. Now take one more step outward. Voyager 1 was launched in 1977. It has traveled for decades without stopping. It is the most distant human-made object ever built. Even so, it has not truly escaped the sun's wider domain in the way most people imagine. The solar system is not just the planets. It includes a vast outer reservoir of icy bodies that may extend tens of thousands of astronomical units from the Sunday. Voyager is far, but cosmic far is cruel. That is the third correction. In space, the most heroic journey our species has made can still be the opening inch of a much longer road. The nearest star, Proxima Centauri, lies about 4.24 light-years away. That number is easy to say and hard to feel, so convert it into failure. At Voyager 1's speed, getting there would take roughly 73,000 years. If human civilization had launched Voyager when the first cities rose in Mesopotamia, it still would not have arrived. our fastest emissary would still be drifting through the dark with no witness nearby. And strapped to that machine is one of the loneliest objects humanity has ever made. The Voyager Golden Record carries greetings, images, music, and sounds from Earth. It is a message in a bottle thrown into an ocean so large that the bottle may never pass another ship. The idea is beautiful. The odds are merciless. Space measures distance. That is the fourth correction. Hope sounds noble on Earth. In interstellar space, hope starts to sound tiny. But perhaps the clearest measure of our smallness is not how far we have travelled. It is how far our presence has travelled. For a little over a century, Earth has been leaking radio and television signals into space. Those signals move at light speed. They are the fastest things we have ever sent. Even so, they have only created a bubble about 125 light-years in radius. That sounds impressive until you place it inside the Milky Way, which is about 100,000 light-years across. Our radio footprint is not a stain on the galaxy. It is more like a breath on a cathedral window. That is the fifth correction. Humanity has not announced itself to the cosmos. It has barely whispered. Beyond that small radius, no civilization could even know we exist from our leaked signals alone. No one farther out has heard our first broadcasts, our music, our wars, our laughter, or our panic. We imagine ourselves as loud because we are loud to one another. The galaxy mostly does not hear us at all. And the Milky Way itself is only one galaxy. That is where the trap snaps shut. Human beings can survive one large number at a time. Moon, Mars, Voyager, Proxima. But scale in the universe is layered. Every local distance that feels unbearable sits inside a larger structure that makes it look small. The staircase keeps rising. You think you have reached the true size of things, and then a larger room opens above your head. So this block is not about travel. It is about isolation. The Moon teaches delay. Mars teaches separation. Voyager teaches insignificance. The nearest star teaches futility. The radio bubble teaches silence. The lesson is the same at every step. Distance is not an inconvenience added onto the universe. It is one of the main ways the universe is built, which means the old question changes shape. It is not only, can we go there? It is what kind of reality makes even the nearest steps feel impossible. And once that question enters your mind, the next one arrives. If our own cosmic neighborhood is already this hard to cross, what does it mean that most of the universe is not full of stars at all, but vast regions of almost nothing? In everyday life, nothing feels simple. A room is full of air, a street is full of motion, a city is full of noise. Even an empty place still contains dust, wind, sound, heat, and traces of life. Space is not like that. That is the first correction. When cosmologists say emptiness, they do not mean quiet. They mean a scale of absence so extreme that the human mind almost refuses to picture it. One of the clearest examples is the Boötes void. It is a roughly spherical region of space about 330 million light-years across. That number is too large to feel directly, so reduce it by comparison. The Milky Way is about 100,000 light-years wide. You could line up more than 3,000 Milky Ways from one side of the Boötes void to the other and still be measuring the same hollow region. And hollow is the right word. In a region that large, astronomers would expect to find thousands of galaxies. Instead, the Boötes void contains only a small number, around 60, with many of them strung along a thin central structure. Imagine entering a continent-sized city and finding only a few dimly lit buildings along one road, with darkness in every other direction. That is closer to the emotional truth of a void. That is the second correction. The universe is not mostly full of stars with a few empty gaps. It is mostly empty, with thin islands of matter scattered through the dark. This matters because our language keeps betraying us. We say outer space and picture a huge black room sprinkled with lights. But the large-scale universe is not a room with decoration. It is more like foam. Vast bubbles of near-nothingness press against thin walls and filaments where matter gathers. The galaxies are the minority. Emptiness is the norm. And the numbers are brutal. Voids are thought to make up roughly 80% of the observable universe by volume. Not 10%, not even half. Most of the cosmos is not occupied by bright galaxies, living worlds, or glowing clouds. Most of it is nearly vacant. If the observable universe were a country, almost all of its territory would be cosmic desert, and the places where matter lives would be narrow border towns clinging to the edges. That is the third correction. Matter is not the default condition of reality. Matter is the exception. The reason goes back to the beginning. The young universe was almost uniform, but not perfectly so. Tiny fluctuations in density were present from the start. Some regions were a little denser than average, others were a little thinner. Gravity took those small differences and amplified them over billions of years. The slightly rich regions got richer, the slightly poor regions got poorer. That process sounds gentle. It was not gentle in consequence. Dense regions pulled in more matter, forming sheets, filaments, and clusters. Underdense regions lost matter to their surroundings and became emptier still. Over time, the cosmic map split into two populations, the places where gravity won visibly and the places where absence kept spreading. The voids were not accidents painted onto a full universe. They were the natural outcome of structure growing unevenly. That is the fourth correction. A void is not a hole punched into reality. It is reality after matter has drained away. The darkness was not added later. In many ways, it was there first, waiting patiently. And here the story becomes more personal. We do not live in a typical bustling region of the cosmos. The Milky Way appears to sit inside an underdense region, sometimes called the KBC void, or the local hole. This structure is far larger than the Bootes void, on the order of roughly 2 billion light-years across. Even if the exact details remain debated, the central idea is unsettling. Our cosmic neighborhood may be less crowded than average. Again, comparison helps. 2 billion light-years is about 6 times the width of the Bootes void. If Bootes feels like a lonely county, the local hole feels like a silent empire. We may be living in the cosmic suburbs, far from the densest traffic, in a place where the lights are already thinner than they should be. That is the fifth correction. Our address may not just be small, it may be unusual. And that unusual address may matter scientifically. Some researchers have proposed that living inside a large, underdense region could affect how we measure cosmic expansion. If matter is denser outside our neighborhood, gravity can pull galaxies outward in ways that make the local universe appear to expand faster than the cosmic average. In plain language, our view might be slightly distorted because we are observing from a sparse district, rather than a typical one. That idea is not universally accepted. The debate remains open, but the implication is powerful. Sometimes the map looks strange not because the universe is wrong, but because the observer is standing in an odd place on the map. That is the sixth correction. Where you are can change what reality seems to be doing. There is also a psychological consequence. Imagine a civilization placed at the center of a great void. Their sky would contain far fewer nearby galaxies. Their telescopes would have less to work with. For much of their history, they might sincerely conclude that their galaxy was all that existed. They would be wrong, but not foolish. They would simply be trapped by their location. That possibility should humble us. We like to think knowledge grows only through intelligence and better tools. But in cosmology, location is part of the experiment. Your address shapes your horizon. Your horizon shapes your theories. What you cannot easily see, you are slow to imagine. So this block is not just about emptiness. It is about perspective. A void is terrifying not because it contains monsters. It is terrifying because it contains almost nothing at all. It is a region so empty that it can erase context. Stand deep enough inside one, and the larger universe begins to disappear from view. Emptiness does not only separate objects. It can separate understanding. And yet the matter that remains did not remain randomly. The galaxies, clusters, and superclusters that survived the draining pull of structure are arranged in a pattern. Thin, connected, enormous. As if all the surviving matter has been pinned to the edges of a hidden design. And that means the next step is even stranger, because the universe is not only emptier than it looks, it is more organized than it looks. The universe does not scatter its matter at random. That is the first correction. When we imagine the cosmos, many of us picture stars and galaxies floating through space like dust in a sunbeam. But at the largest scales, that picture is wrong. The universe has structure. Galaxies gather along enormous filaments. Those filaments intersect at dense knots called clusters. Between them lie vast empty voids. If you could step far enough back to see the pattern, the observable universe would not look like glitter tossed across black velvet. It would look like a web stretched across cosmic darkness. A web is not just a shape. A web is architecture. It tells you that the universe is not merely large. It is arranged. For decades, astronomers suspected this pattern was real. Large galaxy surveys showed that galaxies were clustering in chains and walls, rather than spreading evenly. The maps looked strange at first, almost biological. as if the cosmos had grown like frost on a window. But the data kept pointing in the same direction. Matter was collecting along preferred routes, while the spaces between those routes were draining into emptiness. That is the second correction. The large-scale universe is not a cloud of islands. It is a connected system. Its filaments can stretch for hundreds of millions of light-years. That number is too large to feel directly, so reduce it. A single filament can extend farther than thousands of Milky Ways placed end to end. What looks from Earth like isolated galaxies turns out, from far enough away, to be neighborhoods built along colossal highways of matter. Matter flows along these structures. Gas moves through them. Galaxies form inside them. Clusters grow where the filaments meet, like cities at the junction of impossible roads. The web is not decorative. It is functional. It is the traffic system of the universe. That is the third correction. Galaxies are not the main structure. They are what the main structure produces. For a long time, the cosmic web lived most clearly inside simulations. Supercomputers could begin with the early universe, add gravity, dark matter, and normal matter, then let billions of years unfold mathematically. Again and again, the same pattern emerged. Filaments, nodes, voids. The virtual cosmos kept growing into a web. That was impressive, but it still left an emotional gap. A simulation is not a photograph. It can be correct and still feel distant. Human beings trust images in a way equations never quite replace. We wanted to see the web itself. In 2025, astronomers produced the first direct image of part of a cosmic web filament. The structure they captured stretched roughly 3 million light-years between two galaxies. 3 million light-years is hard to picture, so translate it. Light, moving at 300,000 kilometers per second, would need 3 million years to cross that bridge. Human civilization would have to rise and fall hundreds of times before a beam sent from one end reached the other. That is the fourth correction. Even a single strand of the web is larger than most stories our species knows how to tell. The image came from more than 150 hours of observation with the MUSE instrument on the Very Large Telescope in Chile. Over 150 hours focused on one patch of sky, collecting faint hydrogen glow one photon at a time. That is like staring at one dark field for nights on end, just to catch the outline of a thread larger than empires. The result mattered because it turned a theory into something harsher. The filament was there, not as metaphor, not as artistic impression, as structure. The web had stepped out of simulation and into the record. That is the fifth correction. The cosmos is not a loose collection of bright things. It is a body with bones. In late 2025, researchers reported evidence that one enormous filament, containing a chain of galaxies about 5.5 million light-years long, appeared to be rotating. Not just the galaxies inside it spinning on their own, but the larger filament showing coordinated motion. That discovery was unsettling because filaments were often imagined as passive scaffolding, but roads do not usually turn like rivers. A rotating filament suggests that the web is dynamic. It carries momentum, not just mass. It channels motion, not just location. The structure behaves more like circulation than a silent frame. That is the sixth correction. The cosmic web is not only where galaxies live, it is part of how galaxies are fed, spun, and shaped. And beneath that web sits something even more disturbing. Most of the matter in the universe is not ordinary matter, not atoms, not stars, not planets, not gas clouds. About 85% of matter appears to be dark matter, a form of matter we have never directly detected. It does not shine. It reveals itself only through gravity. Again, comparison helps. Everything you have ever touched, eaten, built, loved, buried, photographed, or measured belongs to the minority. The visible world is the bright skin of reality, while most of the mass sits underneath like an invisible frame. That is the seventh correction. The universe is not built mainly out of the matter you know. The matter you know is the surface. Dark matter seems to have come first. In the early universe, it gathered under gravity before ordinary matter could settle efficiently. It formed deep gravitational wells, and normal matter later fell into those wells, cooling into gas clouds, stars, and galaxies. In that sense, the luminous cosmos is late. The dark scaffold is earlier and deeper. Without dark matter, simulations do a poor job of making the universe we see. The filaments weaken, the clustering changes, the cosmic web loses the strength of its frame. Add dark matter back in, and structure rises with eerie success. It is as if the visible universe is plaster on beams we cannot see. When you look at a galaxy, you are not looking at the whole object. You are looking at the lit portion of a much larger gravitational structure. most of which remains invisible. And dark matter is only part of the darkness. The expansion of the universe is accelerating, which points to something we call dark energy. Unlike dark matter, dark energy does not behave like hidden mass clumping into halos and filaments. It acts more like a property of space itself, driving regions of the universe apart faster over time. Dark matter helps gather structure. Dark energy helps tear distant structure away. Gravity and dark matter pull matter into filaments and nodes. Dark energy stretches the larger cosmic stage, widening the separation between the great structures over time. The universe is building and loosening at once. It is sewing matter into webs, while also drawing the threads farther apart. That is the eighth correction. The cosmos is not simply expanding. It is expanding while sitting on an invisible scaffold and under a force we barely understand. Which means this block is not about patterns in deep space. It is about what the universe is actually made of. The stars are the visible punctuation marks. The web is the sentence. Dark matter is the grammar underneath it. Dark energy is the pressure changing how the sentence keeps unfolding. The Milky Way is not drifting alone through empty space. It sits on a filament. Our local group is not a self-contained island. It belongs to a larger flow. We are residents of a web, clinging to one thread inside a structure so large that even its photographed pieces exceed ordinary comprehension. That should make the next question unavoidable. If the universe has a hidden skeleton, and if our galaxy is only one point along its strands, then where exactly are we being carried inside this larger design? Nothing in the universe is sitting still. That is the first correction. When we imagine our place in the cosmos, we picture ourselves as observers standing still while everything else spreads out around us. But stillness is not our condition. Motion is. The Earth turns. The Earth orbits the Sunday. The Sun moves through the Milky Way. The Milky Way moves with neighboring galaxies. And those galaxies are not wandering at random. They are flowing, as if some terrain is shaping their path. Astronomers noticed this when they measured the motions of galaxies beyond the smooth expansion of the universe. In theory, galaxies should recede from one another with the swelling of space. But many also carry an extra motion layered on top, a drift toward particular regions. That extra motion is called peculiar velocity. The name sounds minor. The consequence is not. That is the second correction. A galaxy is not only moving away with the universe, it is also being pulled through the universe. Our Milky Way, together with hundreds of nearby galaxies, is moving at roughly 600 kilometers per second toward a region in the direction of Centaurus. 600 kilometers per second is about 2.2 million kilometers per hour. At that speed, you could circle Earth more than 50 times in a single hour. Entire galaxies are doing this. Astronomers gave the destination a name, the Great Attractor. That name makes it sound like a single hidden object. The truth is subtler. The Great Attractor is better understood as a gravitational center, a region where huge concentrations of matter influence the motions of galaxies across hundreds of millions of light years. We are not falling toward a point like a stone into a well. We are flowing down a cosmic landscape. That is the third correction. Space is not just emptiness with objects inside it. At large scales, it behaves like terrain, with valleys of gravity guiding motion. Part of the mystery came from location. The Great Attractor lies behind what astronomers call the zone of avoidance, a part of the sky obscured by the dust, gas, and stars of the Milky Way. It is like trying to map a mountain range while standing inside fog. You can feel the pull. You just cannot see the shape clearly. Later observations revealed structures in that direction, including the Norma cluster and farther beyond, the Shapley concentration. These helped explain some of the pull, but the deeper lesson was already clear. Our galaxy is not merely parked inside the universe, it is caught inside a flow. That is the fourth correction. Your cosmic address is not a mailing label. It is a set of moving relationships. So let us build that address step by step. You are on Earth, a rocky planet about 12,742 kilometers wide. That sounds large until you place it beside the Sun, which is about 1.39 million kilometers across. More than 1 million Earths could fit inside the Sunday. Your world is not the stage. It is a grain on the stage. Earth orbits the Sun inside the solar system. The solar system sits inside a region of nearby gas called the local interstellar cloud. And that cloud sits inside the local bubble, a cavity of thin gas roughly 1,000 light-years across. Light leaving one side of that bubble would still be traveling when every empire in recorded history had risen and fallen many times over. That is the fifth correction. Even our immediate stellar environment is too large for human history to matter inside it. The local bubble lies within the Orion Arm, also called the Orion Spur, a minor spiral feature of the Milky Way. The Orion Arm is roughly 3,500 light-years wide and about 10,000 light-years long. To us, that feels like a galaxy. It is not. It is only a side lane. The Milky Way itself is about 100,000 light-years across and contains roughly 250 billion stars. If every star were a grain of salt, the galaxy would become a white landscape, and our Sun would be one grain among hundreds of billions. That is the sixth correction. We do not live near the center of significance. We live on a minor branch inside one ordinary galaxy. The Milky Way belongs to the local group, a collection of about 100 galaxies spread across roughly 10 million light-years. Imagine sending a signal across it. A message leaving one side would arrive long after mountains on Earth had changed shape. Even our group is vast enough to mock the word local. Beyond the local group lies the Virgo supercluster, and beyond that, the basin called Laniakea. Laniakea spans roughly 520 million light-years and contains about 100,000 galaxies. If the Milky Way is one house, Laniakea is a continent of cities, all drifting inside the same gravitational weather. That is the seventh correction. The structures above us do not simply contain galaxies, they organize their motion. And Laniakea is not the end. It is one feature on a larger filament of the cosmic web, one strand in a network that stretches across the observable universe. Every box you think is the final box turns out to sit inside another. This is why cosmic address changes how you think. It removes the illusion of isolation without giving you comfort. We belong to larger and larger structures, but belonging at these scales does not feel intimate. It feels like being carried by a current too large to resist and too large to fully see. So this block is not just about nested labels. It is about surrendering the idea that we stand still at the center of our own diagram. We do not. We orbit, drift, flow, and fall within structures so large that names barely help. Even this address is not the universe. It is only our position inside the part of reality whose light has had time to reach us. And to understand that, we have to go to the edge of sight itself. The edge of the observable universe is not a wall. That is the first correction. Most people imagine the limit of sight as a border in space, as if you could fly far enough and reach some dark shell where everything ends. But the edge of the observable universe is not a place you could touch. It is a limit created by time. The universe is about 13.8 billion years old. So the simple instinct is to say that the farthest thing we can see must be 13.8 billion light-years away. Light travels 1 light-year per year. The math seems clean. The conclusion feels obvious. It is also wrong. That is the second correction. In cosmology, the obvious answer is often the answer that forgets space itself has been changing the whole time. As light traveled toward us, the universe kept expanding. The galaxies that emitted that light were not waiting patiently in fixed positions. They were being carried farther away by the stretching of space. So when astronomers talk about the edge of the observable universe, they do not mean 13.8 billion light-years in every direction. They mean about 46 billion light-years in every direction for a total observable diameter of roughly 93 billion light-years. That number is too large to feel directly, so turn it into something physical. Imagine firing a beam of light across the observable universe from one side to the other. Even though light is the fastest thing in nature, the crossing time would exceed the entire age of the cosmos, and the target would keep receding while the beam traveled. The prison is not made of bars, it is made of expansion. That is the third correction. The observable universe is not just the part that exists, it is the part whose light has managed to survive the race. Astronomers make an important distinction here. There is light travel distance, which tells you how long the light has been on the way. Then there is co-moving distance, which accounts for how much the universe expanded during that journey. One is a travel diary, the other is a map redrawn while the traveler was still in motion. Without that distinction, the universe seems contradictory. With it, the contradiction becomes something worse and more beautiful. You begin to see that space is not a stage. It is an active participant in the story. That is the fourth correction. Distance in cosmology is not a simple ruler laid across a quiet background. The ruler itself stretches while you measure. And when we look all the way out to the farthest light, we do not see galaxies at the edge. We see something older and stranger. We see the cosmic microwave background, the afterglow of the early universe. This radiation was released about 380,000 years after the Big Bang. That sounds early, And it is. If the age of the universe were compressed into a single year, the cosmic microwave background would appear in the first few minutes after midnight on January 1. Everything else you know, stars, galaxies, planets, life, would come much later. Before that moment, the universe was too hot and dense for light to travel freely. Electrons and protons were not yet locked into stable atoms. Photons kept scattering off free particles, trapped in a glowing fog. The early universe was bright, but not transparent. It was like trying to look across a furnace made of light itself. That is the fifth correction. The young universe was not dark, because nothing was there. It was hidden because too much was there. Then the universe cooled. Electrons joined protons. Neutral hydrogen formed. Suddenly, light could move long distances without being scattered at every turn. The cosmos became transparent. The photons released at that moment have been traveling ever since, stretched by expansion from visible and infrared wavelengths down into microwaves. What we call the cosmic microwave background is not just old light. It is the oldest light we can ever hope to see with ordinary telescopes. It is the earliest surviving photograph of a universe that had finally stopped blinding itself. That is the sixth correction. When we look to the furthest edge, we are not seeing the beginning itself. We are seeing the first moment the universe allowed itself to be seen. Beyond that wall of radiation, in the era before recombination, light cannot carry us any farther. There may be information there in other forms. A cosmic neutrino background should exist from an even earlier time, perhaps when the universe was about 1 second old, but we do not yet have the power to read it. For now, light stops at the cosmic microwave background, and our eyes stop with it. That fact is easy to state and hard to absorb. There is a whole era of reality behind that visible curtain, and no telescope using light can cross it. The universe has an archive, but part of it is sealed. That is the seventh correction. Science has not reached the beginning with light. It has reached the oldest page that still remains readable. But there is another boundary, and in some ways, it is harsher. It is called the cosmic event horizon. This is not the limit of what we can see right now. It is the limit of what can ever affect us in the future. Because cosmic expansion is accelerating, some distant regions are being carried away so fast that light emitted from them today will never reach us, no matter how long we wait. This does not violate relativity. Nothing is outrunning light through space. Space itself is expanding. That distinction matters. A person can run on a treadmill and still never reach the wall ahead if the floor moves backward faster than they move forward. Some photons are in exactly that situation. They are sent toward us, but the stretching space between us wins the race. That is the eighth correction. The universe does not only hide its past, it also denies us part of its future. There is, however, a subtle twist. Some regions currently beyond what we can observe may still become visible later, because their light began traveling toward us long ago, before the acceleration fully defeated it. This means our observable volume can still grow somewhat. The future visibility limit is larger than the present observable radius, reaching to objects now roughly 61 billion light-years away. That sounds generous until you compare it to the whole picture. We may eventually see more, perhaps much more than we see now, but even that enlarged view remains a cage. The walls move, but they do not disappear, and over longer timescales, the cage becomes lonelier. Galaxies outside our local gravitationally bound region will continue to drift away. Their light will stretch to longer and longer wavelengths. They will fade, then vanish from practical observation. A future civilization, living trillions of years from now, may look into the sky and see only its own merged local galaxy. No clear evidence of cosmic expansion. No usable microwave background. No easy way to infer the Big Bang at all. That is the ninth correction. We do not live at the end of discovery. We live in a brief and privileged viewing window. Right now, the universe still exposes enough of itself to let us reconstruct its story. The cosmic microwave background is still measurable. Distant galaxies still shine. Expansion still leaves visible fingerprints. We are alive at one of the rare times when the cosmos has not yet hidden too much of its own past. That should make you uneasy, because it means the observable universe is not a permanent gift. It is a temporary allowance. We are looking out from inside a bubble of causality during the short era, when enough signals still overlap to form a coherent map. So this block is not just about size, it is about imprisonment by time. The observable universe is a time prison, because every sightline is controlled by when light was released, how far it had to travel, and how much space changed while it crossed the dark. Some regions are hidden because they are too early, Others are hidden because they are too far and receding too fast. The visible cosmos is not the whole of reality. It is the portion time has permitted to arrive. And once you accept that, another truth becomes harder to avoid. If our visible bubble is this limited, and if even within that bubble the earliest galaxies are already refusing to behave, then what exactly is James Webb revealing about the story we thought we understood? James Webb was supposed to clarify the early universe. Instead, it made the early universe harder to trust. That is the first correction. The telescope built to sharpen the standard story has started to expose the places where the story strains. Webb sees in infrared, which makes it ideal for studying the distant universe. Light from the earliest galaxies has been stretched by cosmic expansion into longer wavelengths by the time it reaches us. Webb was built to catch that redshifted light. It was designed to look backward through time, toward an era when the first galaxies were expected to be small, dim, and only beginning to organize themselves. That is the second correction. The early universe was not waiting quietly for our theories to arrive. It was already prepared to embarrass them. One of the strongest examples is MOM Z14. Its light comes from about 280 million years after the Big Bang. In a universe 13.8 billion years old, that is almost the opening breath. If cosmic history were compressed into one human lifetime of 80 years, MOM Z14 would appear before the child had even learned to speak. It looks bright, compact, chemically active, too early, too finished. Its spectrum suggests elevated nitrogen, which is difficult because nitrogen usually requires generations of stars to form and enrich surrounding gas. Stars must form, die, explode, and seed new stars. But time was exactly what the early universe was supposed to lack. There is another problem. MOM Z14 seems to have already altered the hydrogen around it, helping clear the fog of the early universe earlier than many models expected. The issue is not that it exists. The issue is how developed it seems to be at such a young cosmic age. Webb has found many bright galaxy candidates at very high redshift. Some were later revised downward after follow-up, but even after revision, the pressure remains. The early sky appears richer in luminous galaxies than pre-launch models had prepared us for. In some ranges, the number of bright systems looks far higher than expected, not by a polite margin, but by factors large enough to sound like warning sirens. That is the third correction. When the universe breaks your expectations in the same direction again and again, it stops looking like noise. Zhulong sharpened that feeling. Seen roughly 1 billion years after the Big Bang, it appears large, massive, and structured enough to resemble a mature spiral galaxy. Not the rough draft many models would have predicted for that era, but something closer to a galaxy that has already had time to settle into itself. A galaxy can be bright for several reasons, but organized maturity is harder to fake. Structure takes time. Chemical enrichment takes time. Repeated star formation takes time. Gas must collapse, ignite, explode, recycle, and settle. When multiple objects appear to have raced ahead of schedule, the question changes. You are no longer asking whether one galaxy is unusual. You are asking whether the cosmic clock is being read correctly. That is the fourth correction. James Webb is not merely finding exotic objects. It is testing the pace of reality. The Hubble constant describes how fast the universe is expanding. It sounds like a specialist's number. It is not. It helps determine the age, size, and large-scale history of the universe. Get the expansion rate wrong, and you do not just miss a decimal. You distort the timeline on which everything else depends. One route uses the early universe. Cosmologists study the cosmic microwave background and fit it using the standard lambda CDM model. That approach gives a value near 67 or 68 kilometers per second per megaparsec. The other route uses the nearby universe. Astronomers build the cosmic distance ladder using parallax, Cepheid variables, supernovae, and other local indicators. That route repeatedly lands near 73. 6 units do not sound dramatic to the ear, but here they are enormous. It is like measuring the same heartbeat with 2 precise instruments and getting 2 incompatible rhythms, one calm and one urgent. That is the fifth correction. A small gap in a foundational number can become a fracture across the whole model. For years, people hoped the disagreement would dissolve. Maybe dust was contaminating Cepheid stars. Maybe crowded fields were confusing the measurements. Maybe some calibration in the distance ladder would quietly give way. James Webb re-observed key Cepheid stars in infrared, where dust matters less and the images are cleaner. The result did not restore the old comfort. It largely reinforced the local measurements rather than erasing them. Other independent approaches, including time delay cosmography, using gravitationally lensed quasars, have also leaned toward the higher local value. Different methods keep arriving in the same uncomfortable neighborhood. That is the sixth correction. The more independent routes that arrive at the same problem, the harder it becomes to blame the road. At first glance, they look separate. One concerns galaxies forming too early, the other concerns two expansion rates that refuse to agree. But both point toward the same deeper fear. The standard cosmological model may be incomplete at exactly the level where it claims greatest explanatory power. Lambda CDM still works astonishingly well in many domains. It is not a failed model. It remains one of the most successful frameworks in science. It explains the broad behavior of the cosmic microwave background, the large-scale distribution of matter, and much of the visible universe we actually observe. That is exactly why the present tension matters. Great models do not crack at their weakest points. They crack where reality becomes precise enough to test their foundations. That is the seventh correction. Scientific crisis is not the opposite of success. Sometimes it is what success looks like at higher resolution. Several explanations are on the table. Early dark energy could alter conditions before recombination and shift the inferred Hubble value upward. New neutrino physics might change the energy budget of the young universe. Modified gravity could change how structure grows. Dark matter might behave in ways the standard picture has simplified too aggressively, or our local environment may slightly distort what nearby observations imply. Fix the Hubble tension one way, and you may strain the microwave background. Solve rapid early galaxy growth another way, and you may break later structure that already fits. The danger is not that there are no ideas. The danger is that every idea seems to pay for one repair by damaging another wall. That is the eighth correction. In cosmology, patching the blueprint is harder than patching the room. Not that the Big Bang is false. Not that everything we know is worthless. Not that science has failed. The message is narrower and, in some ways, more unsettling than that. The message is that the elegant timeline we trusted may be too simple. The young universe may have formed complexity faster than expected. The local universe may be expanding differently than the early universe fit predicts. And the bridge connecting those two eras may be missing a piece. But we do know this. When observations from two different fronts both begin pressing on the same conceptual structure, the right response is not denial, it is attention. The universe is not obliged to preserve our comfort. It is only obliged to keep being true. Because if the standard model is under real strain, then the age and growth history of the visible universe may need adjustment. And if that happens, the question we have been circling all night becomes even larger. The observable universe already feels impossibly vast. But what if even our estimate of the larger reality beyond the horizon is attached to a model now beginning to tremble? If the map inside the visible bubble is under revision, then how much larger might the full territory be beyond the wall? The observable universe is not the whole universe. That is the first correction. 93 billion light-years across sounds final. It is not. It is only the part whose light has had time to reach us. Measurements of the cosmic microwave background suggest that space is extremely flat on the largest scales we can observe. Flat does not mean shaped like a sheet of paper. It means our visible patch shows little overall curvature. And that matters because a flatter universe usually means a larger universe. Think of standing on a vast plain. The flatter the land looks around you, the harder it is to tell whether it curves away at all. A small ball shows its curve quickly. A giant world can feel level for a very long time. That is the second correction. The observable universe may look flat, not because it is all there is, but because the larger reality is so much bigger than our window that the curve is hidden from us. Some estimates suggest the total universe could be hundreds of times larger than the observable region. Other inflationary models allow far more, so much larger that the observable universe starts to look like a lit window in a structure you cannot walk around. Inflation says that, in the earliest fraction of a second, the universe expanded at a staggering rate. A tiny region ballooned with astonishing speed, smoothing space and setting the stage for everything that followed. If inflation happened, then our observable universe may be only one local outcome of a process that did not stop everywhere at once. That is the third correction. The Big Bang may not be the beginning of everything. It may be the beginning of our region. In some versions of eternal inflation, space keeps inflating elsewhere, while local pockets stop and form universes like ours. Each pocket becomes its own bubble, with its own history, its own expansion, perhaps even its own physical details. That is what people mean by a multiverse in cosmology. No one should pretend this is settled. It is not. The multiverse sits at the edge of physics and philosophy, but it grows from equations cosmologists take seriously. That is the fourth correction. Some of the strangest ideas in cosmology are not childish. They are what careful mathematics looks like when reality becomes too large for intuition. If the universe is this large, or larger, then where is everybody? The observable universe may contain around 2 trillion galaxies. Each galaxy may hold billions or hundreds of billions of stars. Many of those stars have planets. In the Milky Way alone, estimates for rocky planets in habitable zones run into the hundreds of millions. Scale that upward, and the numbers become absurd. So the silence feels wrong. That is the fifth correction. The Fermi paradox is not born from fantasy. It is born from abundance. If intelligent life is common, why do we not see signs of it? No confirmed signal, no clear artifact, no verified visitation, no unambiguous engineering on galactic scales. Many answers have been proposed. Maybe life is common but intelligence is rare. Maybe intelligent life destroys itself. Maybe advanced civilizations stay hidden. Maybe the universe is dangerous, and silence is a survival strategy. But there is another answer. Maybe the universe is built to isolate. That is the sixth correction. The silence may not mean nobody is out there. It may mean architecture wins before contact begins. Distance already defeats us inside our own neighborhood. Our radio bubble is tiny. The nearest star is years away by light, and tens of thousands of years away by our spacecraft. The galaxy is 100,000 light-years across. A message from one side to the other would take longer than civilizations often survive. Then come the voids, the filaments, the accelerating expansion, the cosmic event horizon. Even if life is common, togetherness may be rare. The universe may contain many islands of awareness, each bright on its own shore, each cut off by water too wide to cross. In any meaningful age of culture, we may not be alone in existence, we may be alone in practice. That is the seventh correction. Cosmic loneliness may be less about biology than about physics. In 1990, Voyager 1 turned its camera back toward Earth from about 6 billion kilometers away. The photograph showed our world as a pale speck in a beam of sunlight, less than a pixel, almost nothing. Carl Sagan made that image famous because it forced a reversal. The photograph does not only make Earth look small, it makes every argument on Earth look small. Every border, every empire, every certainty, every hatred, every triumph, all compressed into a dot, suspended in brightness. That is the eighth correction. Small does not mean meaningless. Small means concentrated. We are tiny by every physical measure discussed tonight. A species on one planet, around one ordinary star, on one filament, in one galaxy, among trillions. And yet we are also the part of the universe that has become aware of the universe. The void does not know it is empty. The web does not know it is vast. Dark matter does not know it is shaping galaxies. But we know, briefly. The atoms in your body were forged in stars. The hydrogen in your water is ancient beyond imagination. The calcium in your bones, the iron in your blood, all of it came from cosmic history. You are one arrangement of the universe, temporarily awake. So this final block is not about despair, it is about proportion. Yes, the universe may be larger than we can conceive. Yes, most of it may be unreachable. Yes, the silence may never break. But the fact that a small world inside one thin thread of the cosmic web produced beings able to ask these questions changes the emotional balance of the story. We are small, but we are the cosmos, briefly able to look back at itself, here.